Okay, let's give you guys some practice. So establish if this series will converge or if it will diverge. So press pause and have a go. Okay, so to do this, we are trying to sum up all the terms. We are trying to sum up all the terms. The way we would do this is we would superimpose a graph on top of it. Superimpose this graph on top of it, and then use Riemann's upper sum to generate all the terms. So basically, using Riemann's upper sum, deliberately create the width here to be 1, create the width here to be 1, create the width here to be 1. So when x is 1, you put it into here. So that will then give you a height of 1 over root of 1, and then you times the width. The width you deliberately created it to be 1. So the area here is 1 over root 1. So when x is 2, put it into here. The height will be 1 over root 2, and then so the height will be 1 over root 2. And then you would times the width, which is 1. So this area here would represent this. This area here would represent this. This area here would represent this. Basically, we are trying to understand this series, but then we would use Riemann's upper sum to just basically to simulate all these terms. So this rectangle would simulate the first term. This rectangle would simulate the second term. This rectangle would simulate the third term, and so on. So we are trying to understand this from 1 to infinity. But then rather than looking at it from 1 to infinity, we would look at it from the first term to some arbitrary nth term. So we would look at it from the first term to some arbitrary nth term. And then later on we can take the limit as capital N tends to infinity. So the minute we take the limit as capital N tends to infinity, then this whole thing here, rather than from 1 to infinity, this whole thing here will then become 1 to infinity. So let me start again. We are trying to understand it from 1 to infinity. But rather than looking at it from 1 to infinity, we would look at it from 1 to some arbitrary nth term, and then later on we can take a limit as n tends to infinity. Then this thing will then become this. Okay, so hang on. So let's just look at let's just look at it from the first term to the capital N arbitrary term. So this thing here would represent this. This rectangle here would represent this. This one would represent this. And for the very last, remember from here to n here, the very last rectangle would actually be n minus 1. Would be 1 over square root of n minus 1. The very last rectangle would be this, because if you use Riemann's upper sum, if you look at this thing here, you would start on the left hand side, jump up to here, and then times 1. If you look at this rectangle here, you would start from the left hand side, jump up to here, and then times 1. So the very last area here, you would look at it, you would look at the left hand side, jump up to here, times 1. So this area here is actually 1 over root n minus 1, which is this bit here. So all the rectangles from the first one to the last one is given by this. Now look at it from the integral perspective now. So this is your 1 over root x graph. That's this red line here. So looking at it from the integral here, so this thing here represents the area underneath the graph here, underneath this line. So the area underneath the line, you can see that the area underneath the line has to be less than or equal to all the areas of the rectangles. So if you look at it, because we're using Riemann's upper sum, all the rectangles must be larger or equal to the area underneath the line, underneath the 1 over the square root of x line. So you can see that this area here, that's this area here, from 1 to capital N, the area underneath that line must be less than or equal to all the rectangles. So you can see that this bit here is slightly more, and so on. So we can say that this integral would be less than or equal to all the rectangles. Now if you look at our notation for Sn is us summing up from here all the way to 1 over square root of n. But then if you look at our simulation only takes us to n minus 1. Only takes us to n minus 1. Our simulation only takes us to n minus 1. But what we are seeking is we are trying to seek from here all the way to 1 over n. What we're seeking is we're seeking from 1 all the way to 1 over root n. We are not, well, currently our simulation only takes us to n minus 1. So we are looking at, so currently we are here, hang on, currently we are here. This thing must be greater than this thing here. This thing here is from here all the way to here. So you can see Sn will have an extra part. Well, Sn having an extra part means Sn must be bigger than this thing here. So because if you look at this is exactly the same as this, but Sn has an extra part. So I can say Sn will be bigger than this. So if Fn is bigger than this and this thing here is bigger than this, then I can say Sn is actually bigger than this thing here. So I can actually say Sn is bigger than this thing here. Okay, so now take the limit. So currently now take the limit as capital N tends to infinity. So take the limit as capital N tends to infinity. Well, the minute you take capital N, take the limit as capital N tends to infinity, then this thing here will become S. So we've done this notation thing before, so you should know the difference between these two. So from here, take the limit as capital N tends to infinity, then this partial sum becomes the actual sum of the whole series. So take the limit, and then when you get to here, you should recognize that this thing here, hang on, you should be able to recognize this. We've done this many times. So remember, if you take the integral from 1 all the way to n, and then let n tend to infinity, this whole thing here, this whole thing here will actually diverge. So hang on, let's go back. Looking at the graph of 1 over x, it will look like this. So if you look at the integral from 1 to infinity of 1 over x dx, this area here will diverge. If you look at y equals 1 over x squared, the graph will look like this. So the area here, the integral from 1 to infinity of 1 over x squared dx, this thing here will converge. If you look, so 1 over x squared looks like this. 1 over square root of x will look something like this. So hang on, will look something like this. So if 1 over x, if the area here 1 over x diverges, then 1 over x squared is, well, from 1 to infinity is slightly bigger. It will also diverge. You should already know this. So this thing here would diverge. Well, S being always greater or equal to this thing here. So if this thing here diverge, if the area gets bigger and bigger and bigger, then S being always bigger than this will have no choice but to diverge. It can't cross over because here it's less than this thing here, but S must always be greater or equal to this thing here. So if this thing here diverge, then this will have no choice but to also diverge. So our series actually diverge. So our series here will actually diverge, meaning the area will, the series will just get bigger and bigger and bigger and bigger. Okay, it will diverge.